Hi guys, and welcome to Learn Extra Live. My name is Indiana and this is Dina. Guys, tonight's show is brought to you by Liberty, and thank you guys rock, and we are so happy that we've been back, well, that we are back, and we hope you all had a fantastic holiday. We missed you terribly, so we hope you missed us as much. So guys, tonight our topic is functions, and Dina will be taking us through it. Please only call and send us questions that are relating to the topic. We will be taking all of the questions in the last 15 minutes of the show. Next week our topic will be functions again, and lots of you have been asking about our schedule. So if you are in a group, the next week's topic is functions again. So tell your friends, tell your study mates, and chat to us on facebook.com/learnextra. Also, our Twitter handle is @learnextra. And so while you're watching, shoot off questions to us. I also have a Casio calculator to give away today, which we'll be giving away tomorrow on the page. So guys, keep your eyes peeled. We also have something exciting happening in today's shows, not telling you which one. So what we'll be doing is that after the break, we'll be getting straight to the lesson with Dina, and we're going to learn more, learn extra, and have an awesome time. See you now.
See you now.
Hi guys, and welcome back to Learn Extra Live. We are so excited to be back with you, and I wonder if you're noticing our snazzy new microphones. I think I look very chic. What do you think? Let me know on facebook.com/learnextra, also on Twitter @learnextra. I just want to give a quick shout out to all the kiddies at Meringue House. Hope you're being good to Mama Salome and behaving yourself. But without further ado, guys, chat to us on Facebook, chat to us on Twitter. We're here to help you. Also, don't forget you can help each other out too. Rafika, I hope you're all joining in and you're all watching. Chat to me. We are now live, finally. So Dina, let's get straight to it with functions. Take it away.
Thank you, Indiana. Thank you very much. And here we are this afternoon to do some work on understanding the word, what it means, what it relates to, and to work with some examples that are going to illustrate that in more depth, and also finally to take some questions from you that relate to functions. Some of you may not have yet covered it in your work, some of you may. However, I do want to say that this afternoon we'll be dealing with some aspects of functions that relate to grade 9 work, just giving them a lovely feel with some new terminology. That's really what a function is. So what I'd like to start off with is by looking at a diagram that simply illustrates the relationship that exists between certain numbers that allows us to call this thing a function. So let's look at the board. We've got over here a set that involves a couple of numbers. We've got a second set and it involves other numbers. Now, if we had to ask ourselves, how does this 1 relate to the 3? How does the 2 relate to the 5? How does the 3 relate to the 7? And how does the 4 relate to the 9? We could have this set having a whole lot more numbers, but our key thing is to say, well, what is that relationship that exists between the numbers? So the word function is really asking us for dictating what kind of relationship governs these two numbers, the 1 and the 3, the 2 and the 5, the 3 and the 7, the 4 and the 9, and possibly others. So if I had to put a 5 in here, what would I get in here that it relates to? A 6, what would it relate to? A 7, what would it relate to? Etc. So a function is basically a set of numbers that exists. There is a second set of numbers that are related to that one in a certain way. And the way that they are related is by means of an equation. And that equation basically is called a very special kind of equation. It's called a function. And so a function in broad terms is really a relationship between a set of numbers. So some of you may have been looking at these numbers and saying, what exactly do I need to do to these numbers in order to get the outcome? And if we go further down, we'll see that I've defined it for you as, firstly, this word element. What is the word element refer to? An element is something that's inside a particular set. So the 1, the 2, the 3, the 4, all these numbers, they are elements. And then I'm talking about another word that you have not seen before, is mapped. Is mapped onto one element of the second set. And by that I mean that there is a direct relationship between the 1 and the 3. So this arrow, this red arrow, indicates a mapping. The 2 maps onto 5, 3 maps onto 7, and 4 maps onto 9. So the number to which that original number relates to, that action is called a mapping. And all this is terminology that you need to know in order to be able to play this game called functions. Without that terminology, we'll be very lost. So let's go through it again. The element is the number inside the set, and this number is mapped onto, is related to the second value. And when this happens, and it relates to just one number, so 1 isn't relating to 3 and to 5, it's only relating to 3. The 2 is not relating to 7 and to 5. It's only relating to 5. So there's only what we call a 1-to-1 mapping. Then we call this relationship a function. So a function is a relationship that exists between two sets where one element from the first set maps onto the element from the second set, and it doesn't map onto others. So you'll understand that if you are going to map onto more than one, that is when we call it a non-function. And we don't have a name for that. We just say that the relationship is then not a function. So we can get functions, we can get non-functions. Functions 1-to-1. Not a function will be when one relates onto two other values. Okay, let's look further. So a function really is saying, what is the, I like to use this word, rule. There is a rule that will govern those numbers. And originally I showed you with this question mark. There is a rule that we have to apply to 1 to get the 3, apply to 2 to get to the 5, 3 to get to the 7, 4 to get to the 9. So there is a rule. And this rule, which earlier I explained to you as an equation, is what we call a function. So it's a mathematical statement that relates to sets of numbers. So I wonder if somebody can tell me, what is the rule that governs this set of numbers? The 1, the 2, the 3, to give us 3, 5, 7, 9. Okay. And I think that if we look just further down and look at what is the rule which connects the elements in set 1 to the elements in set 2, it's actually asking us what is the function. Okay. And okay. So what is the function that governs that set? And if I go back, then we can see very clearly that these numbers, if I take the 1 and I double it, I would get 2. But if I add 1, I get 3. 2, if I double it, I get 4, but if I add 1, I get 5. 3, if I double it and add 1, I get 7, and 4, if I double it and add 1, I get 9. So the rule applies to every single of those numbers. So in other words, if I take, let's write it over here, if I take set 1 and I double it, so I'm going to say times by 2, and I add 1, I get all my numbers in my set 2. So each and every single one of these numbers has to be multiplied by 2, added to 1 to give me set 2. And as you can see, it's very clumsy to do that. You really are introducing words and cumbersome terminology. So what mathematicians have done is they've said, let's make it much easier. Let's give those sets a name. And in naming them with just one letter, we'll be able to talk about it much more in a much more flexible manner. So what we're going to do is call this set, we're going to call the set of x's. And this set, we're going to call the set of y's. And when we do that, then I'm going to be talking about twice of x plus 1, giving me my elements in my second set, which I've called y. Okay? So set 1 is x and set 2 is y. This x, because I'm operating on the set, in other words, I'm not changing between sets. I'm saying set 1 is what I start with. My arrow goes from there to there in each and every case. This set is called the independent set. In other words, we start with that set. And what is it that we must do to each element in that set to get the second set? And therefore, we call the second set the dependent one. Because if we don't have my first set, I can't get the second one. So the second one is dependent on knowing what that first one is. So the first set, where I start independent, we choose, and that one will always be the dependent one. So for the x's, they will be my set of dependent in this case, and my y's will be my set of independent. So very broadly speaking then, a function is a rule that governs two sets of numbers, and those rules, you can have an infinite number of rules, as you can have infinite sets of ways of working with numbers. So except my first set is x, and then my second set will be y. Now, we're going to take a short ad break, and when we come back, I'll go through 3 or 4 more terminology statements with you before we actually go and sketch a linear function. So over to you, Dana.
Fantastic, guys. We're going to take a quick little break. We won't be too long, 2 minutes max. So go get yourself something to eat, something to drink, and be back. I just want to say hello to Koketso, to Shiamo, Kashifa, brilliant. I'm so glad you're all watching. And if you are watching, I just want to give a little shout out. Please come to our Facebook page, facebook.com/LearnExtra. Also chat to us on Twitter @LearnExtra, and help each other out on the page, guys. That's what we really like to see. So we'll see you now, straight after this break. Bye. Hi guys, and welcome back. Grade 10s, I hope you're watching. Grade 11s and 12s, you know the deal. You should be watching too. Guys, I'm about to post the functions and what is a function, what Dina's been working with, onto the Facebook page. So you've got that JPEG that you can download onto your cell phone, and you've always got it and you can share. You know, learning more, learning extra is always cool. So without further ado, we're going to get straight back to Dina. Dina, take it away.
Thanks, Indiana. Right, I spoke about what a function was in relation to a set of values, and I'd like to look at a little bit more of terminology so we can reduce our phrases that we're using and make them really simple. Okay, so the terminology, why is it called functional notation? Well, I spoke to you about a function being a rule that governs a specific or two sets of numbers, and those rules come in variable format. And I'm going to show you now exactly how that looks like so that we can both talk about the same thing. So the first thing is that the rule that we worked with before was 2x plus 1. And I called that 2x plus 1, if you recall, was equal to y. But in the functional notation, you're actually saying that if bracket x is my functional value, that is the dependent value that you get from 2x plus 1. So basically what it looks like is that f is the rule that is governing my set 1 and my set 2 of values. And the independent values that we spoke about earlier, themselves as a unit, they create a set of numbers, and they are called the domain. Let's see if we can shade that in. Yeah, maybe we can shade it in. So your domain, okay, it's not really coming up, so let's just use a red one. All right. The domain is a unit of numbers, and those are your independent values. So back in our original diagram, this here, because it's all the set of x's that we have, this set, the whole of set 1, that is called your domain. It's all the independent numbers that you can put into your rule, or that you can use for your rule. Whereas this second set, the outcomes, the outputs, whatever you want to call them, the values that are dependent on applying the rule to that first set, those values, they've got a unique name, and they are called the range. So going back into our terminology, the domain is a set of all independent values, and the range is the set of all the values in the dependent set. So without the first ones, I can't get the second ones. So the second ones are then called that. But now, because I've called them f of x, and f is known as the rule, this is also brand new for everyone doing this, this set of numbers. The function values will be all my dependent values. So they will be all the outputs. So in our original set, in this set here, these values here, they are all our function values. They're called the function values. Why? Because we only get them when we apply the rule f of x equals, whatever the rule may be. So in order for me to get those function values, I'm going to have function value for 1. So who's related to 1? The 3 is. Function value for 2. Who is related to 2? Function value for 3. Who is related to 3? The 7 is. And function value 4. Who is related to 4? The 9 is. So function value 1 means that the 1 is related to an output, and f of 1. The way you talk is also very important. We talk about f of 1 being who is mapped onto 1. Function value 2, who is mapped onto 2, etc. So very brand new terminology for everybody. And let's go on to and see whether there's anything else that we need to know. Let's go down. All right, so function values are the set of my dependent values, and I will talk about f of 1 equal to 3. Oopsie, let's just take that out there. F of 1 equals 3. Meaning that if you take 1 and you apply the rule to x plus 1, then twice of 1 is 2 plus 1 is 3. So your result that you get from applying the rule will be my function value. And so my function values are often what we call our y values, but they are the answers that you get from a particular rule. And rules can be from anything like 2x plus 1 to negative 3x plus 5 to negative 2 minus 3x squared. There are an infinite number of rules that you can make up. But the way that you relate, you've got to apply it to the set 1 value to get the set 2 value, and my set 2's are then called my functional values. Right, and then what are we talking about when we talk about increasing or decreasing functions? What is known as an increasing function and what is known as a decreasing function. Now, when you looked at that set, as the set 1, as x gets larger from 1 to 2 to 3 to 4, etc., can you see what's happening to the y values or to the function values? They are also getting larger. When that relationship happens, where as x gets bigger and the y also gets bigger, then we basically speak about an increasing function. The function values are getting bigger. But when we get the opposite relationship, if 1 was related to 9 and 2 was related to 7, so if we had the inverse relationship, we were going from x getting larger, but the function values getting smaller, 9, 7, 5, 3, etc., we would then speak about a decreasing function. So it's what's happening to those function values will determine whether it's increasing or decreasing. And you'll see later on when we deal with a lot of functions, questions often, what relationship is it? Is it a decreasing or an increasing relationship? Okay, so let's look at the sketch of f of x equals 2x plus 1. What will that look like? And last year in grade 9, you would have looked at y equals 2x plus 1. Now we've got exactly the same thing, but instead of a y, we've got this new notation, f of x. So how do we read that? F of x, because, okay, f of x. What we're really saying is that the rule is f, and we want to apply rule f onto every x. So of which x are you taking it? So is it f of 1, f of 2, f of 3? Which value on x are we applying that rule? And so we read it as f of x. It's not times x. It's purely a symbolic way of looking at what that functional value is. So here we're asking for all the functional values. It's just, I'm not sure why it's doing that. Okay, so f of x equals to x plus 1 means if y equals to x plus 1, what does this graph look like? And I think that from, let's just look at it in diagrammatic form, actually in picture form, if we had to sketch it. And we've got x and y. Then the y-intercept is 1, because the constant is 1, and the gradient is 2, which means we're going to go across 1 and up 2. And so my line is going to do that. Okay, so this is then known as a linear function. A function that whose rule will give you a set of numbers that when you plot those ordered pairs, you're going to get a line. So this is known as a linear function. Which you're probably thinking, are there other types of functions? Why linear? Well, linear from the root word line. So those ordered pairs that you get from utilizing a specific rule will give you, when plotted, give you a straight line. There are. In grade 10, you're going to deal with 3 other types of functions, and there are many others, but specifically 3 kinds you're going to deal with. And the rules are going to have its own characteristic where you're going to be able to see whether a particular function is in fact going to be linear or not. But linear ones certainly come from your grade 9. We're just giving it a new terminology, f of x equals to x plus 1. And this linear function, then you would put this f on it, because these points all come from that rule known f. If the rule changes, so if we got a new rule and we said the rule was g of x, if we have g of x, then that means I want to go and fetch rule g that I'm going to apply on every x. So the label is purely to identify which function we're talking about. So you could have rule g, you could have rule h, and the most common ones that we work with, it's f, g, and h, but you could get others. It's just a way of talking about a function without getting them mixed up. The symbol really is not anything other than for naming purposes. Right, so we're now going to look at what are the various features of each of these functions. And the features that we would like to look at are things like what are the intercepts? What is the domain? What is the range? Is it increasing? Is it decreasing? So features of any sets of numbers. What can I have for my set 1? What kind of numbers am I getting for set 2? Do they increase or do they decrease? And then I'd also like to know what they look like as sketched. So let's look at f of x equals 3. What would you say f of x equals 3 would look like? F of x equals 3, what would set 1 look like? And what would set 2 look like? So we could say that for every different x, we're having one y value, and that is 3 all the time. And so my function is actually called a constant. Okay, this is an example of a constant function. And earlier on, we said we get increasing or decreasing, but if it stays the same, then we talk about a constant function. So what would this sketch look like, f of x? We would have at 3, there's my constant, because for every single x value, I'm getting one y value. And so that would be my f. Okay? And for g, it would be -3. So that would be g at -3. And so I can get a constant of 3, or I can get a constant of -3. What would h of x equals 3x look like? Well, the y-intercept is 0. So let's take another color and let's try and draw what that would look like. The y-intercept is 0, but the gradient is 3. So I'm going to go across 1 and up 3. So there's my line. Okay. So what kind of a function is it? Well, it can have any x value. It can have any function value, so the domain is a set of reals. But is this a decreasing or increasing function? As x gets larger, my y's are getting larger because I'm multiplying every single x by 3. So I'm tripling whatever I get for x, which, by the way, are known as your abscissa. So if we wanted to really be smart about our definition of domain, then it would be the set of all abscissae, and the range would be the set of all ordinates. Okay, so 3x means I'm taking every x value and I'm tripling it. So the multiples of 3 is what this green line is referring to. As my x increases, so my multiple of 3 is getting bigger, and hence this would be an increasing function. Let's try and get another color. Let's go for red. And, okay, so let's go white. Okay. Okay. Right, so -3x would be this line. Can you see what's happening now? Is that as x is getting bigger, as x gets bigger, my y is getting smaller. So what I then am able to explain about those y values is that they're getting smaller and smaller and smaller. Therefore, that is known as decreasing. So that's an increasing function, that's a decreasing function. And you'll notice that a positive gradient will be increasing, whereas a negative gradient will be decreasing. Okay, we'll leave those for a little later. Let's go off to an ad break, and then we'll take some of your questions.
Fantastic. So guys, if there is anything that you're not understanding, please let us know on our Facebook page. We will be taking in the last 15 minutes of the show. I can't believe that the show has gone that fast. So without wasting any time, we're going to take a quick break. And while we're doing that, get those questions posted on the page. Please, please, please. And don't forget, you could win a Casio calculator to get those questions posting. See you now after the break. Hi guys, and welcome back to Learn Extra Live. I hope that you're really enjoying the grade 10 show as much as I am. I'm so glad to be back, guys. I'm so happy to see that you are all rocking out on the page. I just wanted to say, Koketso, she said that she's just gotten back from camp and she had an awesome, awesome time. She's just a bit tired, but she's amped for maths. So guys, let me know, what did you guys do this holiday? Did you get up to anything exciting? Don't forget to chat to us on facebook.com/Learn Extra. Also chat to us on Twitter @Learn Extra. I just want to give a big shout out to Liberty for being so awesome and making this show possible. So Dina, I think we're going to go over a few more things. And guys, don't forget, if you've got questions, please, now is the time to send them through. Dina, take it away.
Thank you, Indiana. Let's have a look at what I was doing with you just a little earlier. I've just relabeled my axes so that we can see the various gradients and how they actually tell us what the function values are as well. So let's have a look at the, let's go up 1, the h of x equals 3x, okay? So here's h of x equals 3x. What does that mean? Is that there's a rule, and the rule is called h, and the rule is triple every single number in your first set by 3. So every number will be tripled, and your outcome, your multiples of 3, will now have been generated, and that you put in your second set. So every single multiple of 3 becomes the range, and your first set, all the x's that you put into your set, that will be called the domain. Now, if I had to plot those, then it would be something like this, where we would have our x values and we would have our h of x values. Okay. So I'm not going to tabulate them because the board's not really working that well. So let's come back here and say that if x was 1, for example, our multiple of 3 would then be 3. If x was 2, then if I times 3 by 2, remember to use the rule, 3 times 2 is 6. So we'd go up to 6. If x is 0, then we'd have a 0. We've just lost our color. Okay. If x was minus 1, then to triple it times by 3, we'd get minus 3. And if we join those points up, we would then get the straight line that goes through those points. This rule we've called h. Okay. So the function is the rule function h. For every x, there is an h of x value. And if x was 1, then this would be 3 times 1. If x was 2, then this would be 3 times 2. If this is 3, then it would be 3 times 3, etc. So my rule is to triple every single number 1, 2, 3. Once you've plotted them, then because of the nature of that rule, because I've only got an x to the power of 1, that will automatically give me a straight line. Okay. If I take the power of that x to be 2, it's not going to be linear. It's going to be something else, but not linear. So the power of 1 indicates that it will be linear. Okay. So h is the rule. What about k of x? Let's just choose another color. Let's go k of x equals minus 3. The rule is called k. I'm going to apply the rule onto every x, and I'm going to get the output. The output will be to take x and multiply it by minus 3 this time. Not to multiply it by positive, but multiply it by negative 3. So if I do that, 1 times negative 3 is negative 3. 2 times negative 3, 1 times negative 3 is negative 3 here. 2 would be negative 6, which is going to be down there. Then I'm going to get the 0. Minus 1 times minus 3 is going to give me 3. If we join those points, we have created all the possibilities of those ordered pairs that come from applying rule k. So every line is a set of numbers that is a set of coordinates that allows you for set 1 and set 2 the input as well as the output values. So that would be the green one. Now what would m look like? How could we use the yellow graph to construct what is happening with that rule m? What is rule m? Well, let's read it. It says triple x, but then you must take 3 away. So what would you do to the yellow values that would give you a new rule? Because it's not the same one, it's been changed. So it's called rule m. Let's choose this one. Okay, this is rule m. How could I use the yellow one in order to sketch the blue one? Okay. Right, so at 1, we've got a 3. But now they're saying, please, won't you minus 3 from it? So we've got to take 3 away. So at 1, we'd get 0, because we've had to take 3 away. What would happen at 2? That was 6. And we've got to take 3 away, so it would be 3. So 2 would be 3. What would happen at 0? We've got to take 3 away, so we'd be at minus 3. So you can actually see that all the y values on the yellow line have actually decreased by 3. But what's so amazing is if I sketch through those points there, is that this white line is now my new rule m, And we see something very important between the yellow and the white line. Something that you can actually look at between the yellow and this, or actually the rule, the yellow rule, which is 3x, and this rule here, which is 3x minus 3. So there's something happening algebraically, and there is something happening on the picture. And that something is that these two lines are in fact parallel. And they parallel because those coefficients are the same for x. So the coefficient of x will always determine what the gradient of the line is. And when the gradients are the same, then the lines will be parallel. So something that's happening in algebra is actually visible on a graph. So functions or rules that have the same coefficient for x in the linear sense will always be depicted on a graph as parallel lines. So what about this p of x? What about this rule? And I guess that, yeah, okay. What about p of x? If I had to rewrite this, then it would be x over 3. And to every single grade 10 out there, want to find out what is the coefficient of x in this case? Is it 1? Is it 3? Is it a third? It's very important to know that in fractional form, the coefficient is always a fraction. So the coefficient of x isn't 1. The coefficient of x in this case is a third. So my gradient is a third. So what I'm saying is that the rule is to take every x and to multiply it by a third. In other words, it's to take x and to divide it by 3. So take a third of it. Okay? So if we took x of 0, it would still be 0. If we took minus 3 and we took a third of it, we'd get minus 1. Okay? And if we took 3 and took a third of it, we would get 1. So I'm now going to draw this line through all these points here. And this is our rule that we've called P. Anything special about P and the white line? No, nothing special. What about the yellow? Don't think so. But something happens between the white and the green line. Anyone remember what that relationship is between that white and that green, and why it is so? So it's saying that there's something special happening between these two. Okay? What is it? Firstly, this coefficient is negative 3. This coefficient is a third. If we look at those lines, the green and the white one, they're actually perpendicular. Okay, so linear functions that have rules, which are just functions, but linear functions which have one, a coefficient, and the other one's coefficient is a different sign and the reciprocal, then those lines will always exhibit perpendicularity, or we say the functions are perpendicular to each other. So there is an algebraic component to functions as well as a graphical component to functions. One can't go without the other. So we have P, we say P is perpendicular to K. And so we talk about function P being perpendicular to function K because the gradient of P multiplied by the gradient of K will equal to negative 3 times a third will equal negative 1. And so that concludes the terminology around functions. I would really like to look at some of your Facebook questions, so let me send you back to Indiana.
Fantastic. So guys, if you haven't sent me a question, please send them now. We've got, I think, 10 minutes left, but let me start with the ones that we do have. Okay, let me have a look here. Give me 2 seconds. Okay, so I think it's Blair. Blair's question is based on the increase and the decrease. What would it be called if it was a curve? And we've actually got Kashifa, because I know Kashifa's quite, she's in grade 12 and she's always on the page, and she's one of our top mind setters, and she said you'll learn about that later. So Smarkle obviously knows it's coming later in the syllabus. Dina, should we chat about it?
Yeah, we can chat about it.
Okay, so.
Okay, let's chat about it. I've defined for you increasing and decreasing not in the sense of just the linear function, because remember, functions are rules, and rules aren't necessarily linear. We can have any rules. The rule I've discussed with you today is called the linear function. But when I started talking about functions, I started talking about them in general. So whenever you have, let's go back to the first page where we had the relationship increasing in your output values, that will always be a increasing function. So when you have a curve, and if we had to sketch a curve, let's go here and sketch a curve. Let's go down here. And let's talk about a curve doing something of that nature. Okay. Then as you go from left to right, this value, at this value here, the function does some kind of turn. So we would describe part of the function over here as decreasing. Then it turns, and then from this value to that value, it then increases because the y values are getting larger. And then from here to that point there, it would be decreasing, and then would be increasing. So you would actually look at various portions of the curve in order to describe what would be happening to that curve at those places. So we actually break the curve up and establish when is it decreasing, when is it increasing. But the increasing and decreasing all depends what is happening to the y values. That's really what you must remember.
Okay. So this one I think is a good question because 3 mind-setters, Tishiamo, Cassius, and Lebogang, said they're struggling with this. They said they're lost, and they've said h, open brackets, x, equals 3x, question mark, totally lost, please help. There you go. Yeah, help is on its way.
Let's have a look at that. I think it was over here. Okay, so it was on this page. H of x equals 3x. Okay, so I'm going to try. Okay, let's go for an ad break.
Okay, should we?
Yeah.
What we're going to do, guys, we're going to go for a quick ad break because we like to keep you in suspense like that just before we're about to answer the question. We'll get to it straight after the break. See you then. Hi guys, and welcome back to the last 10 minutes of Learn Extra Live Maths, grade 10s. I hope you're watching and you're hanging on to the edge of your seats. We were just about to go over a question. So guys, I think what we're going to do without further ado, we're going to go straight back to Dina. Dina, take it away.
Thanks, Indiana. You were asking earlier about h of x equals 3x, and you are just asking question mark, where does that come from? Where's it going? How do we use it? Okay, so let me go through it again. H is the name of the rule. Like you have a name, the rule has a name called h. And you are going to have a set of values called x that you're going to be operating on. That's called set 1. And your rule comes straight after that. Your rule says 3x. So the rule is saying that we must take every single x value that we would like to have in our set and then triple it. So that we'll have a starting set and the ending set. So let's look at what a table of values would look like. So if x was 1, for example, the rule is that we've got to take h of 1. So you're going to apply the rule to every single x value. And that h of 1 is what we call the function value. So you've got to get your mind around the fact that these things have got names and what do they depict? What are they? So h is the rule. What is the rule? 3x. So for every x value, you're going to take 3x. So this is going to be 3 times 1. Because the rule is to triple that x value. If x is 2, then h of 2 is going to equal to 3 times 2, which is equal to 6. If x is 3, then h of 3 is equal to 3 times 3, which is equal to 9. If x is 4, then h of 4 is equal to 3 times 4, which is equal to 12. So my independent set is the set I've chosen, and you, as a mathematician, will always choose those x values. You've got to decide what it is that you're using. Once you know what value it is, then you apply the rule, which is to triple that value. Somebody's going to give you a rule. That rule's got to come from somewhere. Either you've made it up or somebody's given it to you. So 3x is our rule. So for 1, I'm going to triple 1, I get 3. For 2, I'm going to triple 2, I'm going to get 6. For 3, I'm going to triple 3, I'm going to get 9. For 4, I'm going to triple 4, I'm going to get 12. So that's what that is. And now to plot those points, if I plot the point 1, 3, 2, 6, 3, 9, 4, 12, when I plot all those, they're going to fall into a line because that's an example of a linear function. So once you've got your function values, you would then plot your abscissa with your function value. So on your graph, you would have, let's say, 1, 3 as a point, or we could even have -1, -3, and this point here would be my x, and my y value is now called my f of x value, or my function value. So that's a position for the function value is the y value. I hope that helps. Indiana, what else?
I think it did. Well, we actually had a question from Vandal, but I see that Kashifa has actually answered for us. I think we've actually answered this question by doing this. So let's see if we can find some new ones here. Okay, we've asked about the curve, right?
The curve, yeah, the increasing, decreasing curve.
Exactly. So hopefully you guys were watching.
It all depends on the function values getting larger or getting smaller. Yeah.
And then Tapelo said, "Oh, now I get it. If the coefficient of x is negative, then the graph declines." Smiley face. so glad you're getting it, Tapelo. This is fantastic. Guys, I know that I've got a question. When are the repeats? The repeats are on the weekend. Okay, so now this one is from Koketso, and hopefully she isn't confusing herself. She says, "So another Q, are we always going to plot a graph for this? And is this more like a Q-plane, where we solve first, then plot, or get a question from graphs? Maybe I'm confusing myself." Does that make sense?
What does she ask first?
She says, "Are we always going to plot a graph for this?
Yes.
And is this more like a Q-plane, where we solve..."
A Q-plane, yeah, a Cartesian plane. Yes, yes. Okay, let me address that. Yes, functions are very much on the Cartesian plane. You can't have a function if you're not talking Cartesian plane. So, okay, so the Cartesian plane, basically, you're going to have a number of, let's put it over there. There's my rule H. It's my rule H. There's my rule M. And you're going to firstly have to graph them, and you're going to be able to interpret questions from the functions. So it's a different, remember I said, a different terminology that allows you to name these things in a different sense. And only when you get to grade 12 will you really see the benefit. For now, it's up to you to really groom yourself in the terminology, because the benefit will come a little later. Also, when you sketch will be given to you, and you'll have to answer questions from the actual functions. And next week, I know that you'll do a lot more on functions, and you'll see how we apply the terminology to it as well. So come back for next week for some more.
Exactly, guys. So see you next week for functions. Thank you so much, grade 10s, for a fantastic lesson. Grade 11s, don't forget that you are next. Had a fantastic show. Yay for the first show since being back. See you same time, same place next week. Bye.